In this question, a student has a sample of pure water. So let's go to our table over here and find water. Here's water. So all the information we need is going to be in that bottom row for our table for this question. First, we're asked, what is the freezing point of pure water? So freezing point is in this column of our table here. So this is going to be our freezing point of pure water. So we can fill that in here. It's 0 degrees C. Okay. Next, we're told that a student dissolves 2.57 moles of barium bromide, BaBr2, in 1 kilogram of water. And our goal is to figure out the freezing point of the solution. So when things get dissolved in pure substances, it changes the freezing and boiling points. So these are all the factors that are going to affect how much that changes by. I is the Van't Hoff factor. The Van't Hoff factor tells us how many particles of solute we end up with in our solution based on one formula unit of it being dissolved. So in this question, we have BaBr2, our ionic compound. When this dissolves, we end up with 1 Ba2 plus in solution, and we end up with 2 Br minus. That's why we've got BaBr2 as our formula. So when one formula unit of BaBr2 dissolves in water, we have 1, 2, 3 solute particles now dissolved in our water when it dissociates. So I, the Van't Hoff factor, is going to be 3 for this ionic compound. Next, we have this italicized M. That stands for molality, which is similar to molarity in that it's a measurement of our concentration, but it has different units. Molarity, which we normally use, is moles per liter. But molality is moles of solute per kilogram of solvent. So here we had 2.57 moles dissolved in 1 kilogram of water. So our molality is going to be 2.57 moles per kilogram. So our molality there is 2.57. K, that's going to be either our freezing point depression constant or our boiling point elevation constant. So looking at our question, we're asked about the freezing point. So we're going to be looking at Kf over here. Kf is our freezing point depression constant for water. So we're looking at our bottom row on our last column, which is 1.86. So we can fill that in here. And that's going to be different for different substances. So make sure you're looking at the correct substance. Here we've got water, which is why we've chosen 1.86. Lastly, we can use these to calculate the change in the freezing point for pure water. So let's head to our reference sheet and find an equation. Here's our equation for boiling point elevation and freezing point depression. Delta T equals IKM. Let's write that down. Delta T equals IKM. So we're going to put in our values for I, K, and M to find the change in the temperature. It's 3 for I, 1.86 for K, and 2.57 for M. Remember, that is an italicized M. That's our molality, not the mass. If we put those all into our calculator and calculate that out, we're going to get 14.3 degrees C as our temperature change. So we have 14.3 degrees C. Our final step is to figure out what would be the freezing point of this solution. Now we know it's changed by 14.3 degrees. And if we go back and look again at our equation, it's the boiling point elevation and freezing point depression equation. So if we're talking about a boiling point, it's going to be elevated, which means higher. So a boiling point will be that much higher than the pure boiling point. With freezing point, it's depression. Depression means lower. So our freezing point is going to be lower than our original pure freezing point. So if our original freezing point was 0, and then it got lowered by 14.3 degrees C, then our freezing point of our solution is going to be negative 14.3 degrees C. So to get that, we're taking our original freezing point and subtracting the change that we calculated with our equation. So we end up with negative 14.3 degrees C as our freezing point of the solution. Let's do one more question of this type. In this question, we have a sample of pure cyclohexane, which is here in our table. So we're going to be using that top row. We're asked about the boiling point of pure cyclohexane. Boiling points are in this first column. So this is going to be our boiling point of cyclohexane, 80.8 degrees C. So we can fill that in here. We're then told that a student dissolves 0.759 moles of propane, C3H8, in 1 kilogram of cyclohexane. And our goal is to figure out the new boiling point of this solution. Okay, so our first step is looking at I, our Van 't Hoff factor. Remember, that's how many particles of our solute we end up with in the solution per formula unit of the thing that's being dissolved. So we have propane, which is C3H8, being dissolved in cyclohexane. Now, propane isn't an ionic compound. It's a covalent compound. So when propane dissolves, it does not split up into its ions. It doesn't have ions. It stays as it is. So when this dissolves in cyclohexane, it stays as molecules of C3H8. So for every one C3H8 that gets dissolved, we end up with one particle, which is C3H8, in the solution. So our I is just going to be 1 for this because it's a covalent compound. It doesn't split up into its ions. M, that italicized M is our molality. That's moles per kilogram. And in this question, we had 0.759 moles of propane in 1 kilogram of cyclohexane. So that's going to be our molality, 0.759 moles per kilogram. K, that's either going to be our boiling point elevation constant or our freezing point depression constant. Since this question is about boiling points, we're going to be using KB, which is our boiling point elevation constant. For cyclohexane, that's 2.79. So we can fill that in here. And finally, we can put all that into our equation, which is the same as last time. To find our change in temperature, it's going to be I, which was 1, multiplied by K, which is 2.79, multiplied by italicized M, which is the molality, moles per kilogram, which is 0.759. And if we put all that into our calculator, we're going to get out a temperature change of 2.12 degrees C. So let's test that here, 2.12. Awesome. Okay, so we know that our boiling point is going to change by 2.12 degrees C. So finally, we're asked, what is the boiling point of the solution? Well, our initial boiling point was 80.8 degrees C. That's for pure cyclohexane. Then we added the propane, and that causes the boiling point to elevate or increase, since KB is the boiling point elevation constant. So we're going to add our temperature change, which was 2.12, and calculate that to get our final boiling point for this solution, which is 82.9 degrees C. So we can fill that in here. So in this question, you're using the information from the table and using information about your solute molecule to figure out what the change in the temperature of the boiling or freezing point is going to be. If it's a freezing point, it's going to be depressed, which means get lower. So you're going to subtract that freezing point from the original freezing point for pure substance. If it's a boiling point, the boiling point is going to be elevated, which means increased. So we're going to be adding that temperature change to the pure boiling point to get the boiling point of our solution.